One common violation of Hardy-Weinberg equilibrium conditions is selection, or put another way, fitness. What fitness refers to is that not all genotypes are equally able to survive and reproduce in a given environment. Let's just take a hypothetical population that is in Hardy-Weinberg equilibrium to start. Let's give it P equal to 0.8, Q is equal to 0.2. Therefore, in this population, we would have P squared, or 0.64, big A individuals. We would have 2PQ, heterozygous individuals. So that's 0.8 times 0.2, 0.16, so 0.32 for the heterozygous class. And then Q squared, little a individuals, which 0.2 squared is 0.04. Now, as a check, to make sure that you've done that correctly, you should add these up. So 0.64 plus 0.32 is 0.96 plus 0.04 equals 1. So that should add up to 1. So here's a population in its starting point that we'll say has met Hardy-Weinberg equilibrium conditions. Now let's do a thought experiment where we say, okay, when this population now reproduces in this environment, say there's been some environmental change, where now the relative ability of these genotypes to reproduce in this environment has changed. Let's say that 100% of the big A individuals reproduce just fine. 100% of the heterozygotes reproduce just fine. But now in these new environmental conditions, only 0.5 of the little a individuals are able to reproduce. We would now say that the fitness of the little a genotype is now 0.5. It's reduced to half compared to what we would see in the other genotypes. So what you can do to apply a selection step is to carry each of these through and say, okay, 0.64, well, of all of those reproduce, then that will be the starting point in the next generation for that genotype. 0.32 for their heterozygotes. But now only 0.5, the reproductive capability of this genotype is only half of what the other ones are. So what we will do is we will say this is now reduced to 0.02. Now, it's not appropriate just to leave these values as is, because these values no longer add up to 1. We need to normalize these values up to the new total. So the way that this is done is to add these values together. So this now totals, so we could say the total is now equal to 0.98 because we've lost 0.02 along the way. And the new value, the new frequency of the big A individual class, or the big A genotype, is now 0.64 out of this new total of 0.98. Likewise, 0.32 divided by 0.98 and 0.02 divided by 0.98. So this is simply normalizing these values to the new total. Instead of being out of a total of 0.98, we can now take this whole thing out of a total of 0.1. So now we just do the number crunching. So 0.64 out of 0.98 comes to about, and now you're going to have to round a little bit. Say that's 0.653 plus or minus 0.32 out of 0.98. This is 0.326-ish, somewhere in there. 0.02 divided by 0.98 gives us 0.02 and 0.04. I realize I'm not being consistent with sig figs, but that's okay. For the purposes of what we're discussing, we're just attempting to show a shift in allele frequencies over time. So what you can see is, in this population, we have a shift. We've lost some little a alleles as a result of the selection step, and because of that, these alleles have become less frequent in the population, and the other alleles, the big A allele, has become slightly more frequent. So here's the new population after one round of mating in the new selective environment. Let's now determine the new P and Q values. So simply based on this. So if that's the frequency of the big A class, heterozygotes, and little a class, we can use the same principles that we've used prior to calculate allele frequencies. So the frequency of the big A allele is the frequency of the big A class plus 1/2 the frequency of the heterozygous class, which is, in this case, 0.653 plus 1/2 times 0.326. So let's just crunch that. And again, there's going to be some rounding issues here. So that comes out to about 0.816. And so that was P equals that. Q is equal to the frequency of the homozygous recessive class plus 1/2 of the frequency of the heterozygote, which is equal to 0.0204 plus 1/2 of 0.326. And that comes out to approximately 1.184. Well, 34. Again, there's some rounding issues here. But the point that we're making, the trend that we're seeing is P used to be 0.8 in the prior generation, and now it's increased slightly. We've got slightly more big A alleles in the population, and that's because we've lost primarily little a alleles by the failure of some of these individuals to reproduce. Likewise, the value of Q has dropped. So Q is now down to 0.18 or so, whereas it was 0.2 before. So this is a selection step, and what we could do if we wanted to, if we called this P prime and Q prime, whereas this is P and Q, we could carry this on to a next generation and determine P prime prime and Q prime prime and so on, down to as many generations as we care to determine what the genotype trend is. If you track this far enough, eventually, as this goes to infinity, if nothing changes, you would expect the frequency of Q to eventually approach 0. Another violation of Hardy-Weinberg equilibrium conditions arises out of non-random sampling. So this is sometimes referred to as genetic drift as an example, and one particular example of this type of effect is known as the founder effect, which is something that we'll describe now. So let's assume a population exists that's in Hardy-Weinberg equilibrium. Let's use P equals 0.5 and Q equals 0.5 for this population. This population has the following distribution of genotypes. Okay, which adds up to 1. So imagine if this is a large stable population, say on a mainland area, and then let's say there's a small island. So here's the mainland population. There's a large population here that has this particular genotype distribution and this P and Q value, and it remains stable over many generations because Hardy-Weinberg conditions are met. Now let's say a small population from this mainland population manages to make it over to the island and found a new population there. And let's just say that there are 6 individuals who are big A that make it over, and 2 that are heterozygotes, and no homozygous recessive individuals make it over. So 0, little a. And these 8 individuals found this new population on the island. This population has a different P and Q value from the mainland population simply by virtue of the fact that this was not a representative sample of the larger population here. So whereas this population has a p and a q value of 0.5 each, we can now calculate the new p and q value for this small population. So in order to calculate the new p and the new q values for this small population that's gone over to the island, we apply the same principles that we've done thus far. So now we have 6 out of 8 that are big A, which is 0.75, and we have 2 out of 8 that are the heterozygous class, so that's 0.25, and then again no little a individuals in this population. So if that's the frequency of the big A class, that's the frequency of the heterozygous class, then we can calculate P for the island. I'll do this as a superscript capital I, is equal to 0.75 plus 1/2 of 0.25, and Q for the island is equal to 0 plus 1/2 times 0.25. Okay, so let's just crunch those numbers. So 0.25 times 0.5 is 0.125 plus 0.75. So this is 0.875 for the new P value on the island. And then the Q value is simply 0.125, half of 0.25. And again, as a check, those should add up to 1. So simply based on non-random sampling, a non-random sample that founds a new population, you can have a shift in P and Q for that new population simply based on non-random sampling. Now, if there are no selective pressures on the island, if this population is able to maintain Hardy-Weinberg equilibrium conditions, then this going forward will be the new population P and Q value. You might want to predict, okay, well, what will the frequency of the different genotypes be now that we have this P and this Q value for the island? And that's what we'll do in the next segment. So in this case, we would expect P squared, so Pi now dealing with the island, P squared, which is 0.875 squared. So this will be approximately 0.7656. So we would have this many individuals that are big A in the first generation, that proportion. We would have 2 PQ on the island, and that would be 0.875 times 0.125 times 2. So this will be approximately 0.2188 that are heterozygous. And then we would expect Q squared for the island, which is 0.125 squared. So we would see 0.0156 approximately on the island that are homozygous recessives. So this would be the new genotype frequencies, assuming that Hardy-Weinberg equilibrium conditions are met on the island. And that is markedly different than what we saw on the mainland due to this non-random sampling or the founder effect that produced this new population.